Okay, welcome back. This is P-Dog with lecture 5.3 of chapter 5, which is the electrons and the quantum mechanical model. And we are finally going to talk about the physics behind all this stuff. And so here we go. Our objective for this is as follows. The students will understand the basis for the quantum mechanical model of the atom. This is how we get it. So, we start with light waves. And light travels by waves similar to the way that waves move a boat. Light waves are actually electromagnetic waves and a very small portion of the total electromagnetic spectrum. Okay, and so we have these characteristics of waves, and they are as follows. The first is the amplitude, given by this over here. The amplitude is the height of the wave, from the center line of the wave all the way to the top. Okay, then there is the wavelength, which is the distance between crests, or it's really a cycle. It's the distance between any two corresponding parts of the wave. So notice how this right here is on the downside. As the wave comes down to right there, it's on the downside of the wave, and it goes down and then back up and back to the downside in the same height, in the same the same corresponding part of the next wave. The distance between those two is the wavelength. So it doesn't have to be crest to crest. It doesn't have to be trough, which is this guy down here. This would be a trough. This point right here. This is a crest. Okay. It doesn't have to be crest to crest. It doesn't have to be trough to trough. It can be any two corresponding parts of the wave. All right, then we have the velocity of the wave, and that's how fast the waves move past a particular point, and that is given by v. Now, for light, there is a particular v. V equals c. Okay, for light, v equals c, and c is the speed of light that we've mentioned before, which is 3 times 10 to the 8th meters per second, which is really smoking fast. 300 million meters in 1 second. Okay, now this c equals the wavelength of light, which is given by lambda. That's this symbol right here, lambda. And frequency, which is a script f, or there's another symbol for frequency, and it is called nu. And it's this little, it's kind of a squiggly V, like that. And that would be nu. And let me draw that more clearly. That would be nu. And this is pronounced nu. And that's the same thing for frequency. Lambda f or lambda nu. And that is the comparison between the speed of light, the wavelength, and the frequency. And this frequency then represents the energy. So, in our electromagnetic spectrum, the amplitude determines the intensity of the wave. So think about loudness of sound. That would be the amplitude of the sound. That's the same thing as brightness of light, would be the intensity. Okay, the shorter the wavelength, the more energy and more penetrating the ray. So gamma rays have a really short wavelength of 10 to the negative 11th meters to radio waves, which are 10 to the negative 1 meters. So as far as, a decimeter is the wavelength of a radio wave. Visible light, in other words, like white light from a light bulb, actually has an infinite number of colors in it, but is generally categorized as Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. These colors are fractionated out with a prism, or like raindrops, which make a rainbow, or a double rainbow, all the way. Oh my gosh! or the diffraction gratings that we used in class. And so that also fractionates the light. Now, there's an interesting story about this. Note Isaac Newton, when Isaac Newton was actually the person that figured out how to do this, how to fractionate the light and how to create a rainbow from white light. And when he did, he found that the colors were actually red, orange, yellow, green, blue, and purple. But he was a very devoutly religious man, and he could not accept that the creator would have made a spectrum, something so beautiful as a rainbow, with a number of colors that is so close to an evil set of numbers from his beliefs. And so he created the idea of indigo, which is just really a dark blue. And because he wanted to have that seventh, which is a much luckier and much more theologically friendly number. So the true spectrum is red, orange, yellow, green, blue, and violet. And you guys know this when you have you create your color wheels. So there's red, okay, and then there's orange, right, and then there's yellow, okay, then there's green, then there's blue, okay, and then there's violet. And those two don't look very different, so let's come up with a different orange here. How about that? That looks better. And let's do this one for red, so it's even a better red. Okay, so you have those colors, and we know that red and green are opposites, and purple and yellow are opposites, and orange and blue are opposite colors, and that we mix them, and we mix red. And so 6 works for our purposes of using colors. But Isaac Newton couldn't handle that, and so he had to throw in this seventh color, indigo, right there. And so this is another one of the instances where personal beliefs affects the actual science of what's going on. Okay, now our visible spectrum is from 400 nanometers to 700 nanometers in wavelength, which is in the 10 to the negative 7th meter range, and it's a very narrow range of wavelengths. And if you look at a electromagnetic we'll see, which we've done in class. You see that our actual visible light is very, very small compared to the entirety of visible light. Now, you may be asking yourself at this point, and I want to go over this at this point, how is it then, or how do we go from the frequency of light to representing a certain amount of energy? And so I'm going to talk to you about that right now. Oh, which leads us to the bright line spectra. Okay, a bright line spectra that we've already looked at in class is a spectrum that contains only certain colors or wavelengths of light. Now, each element, when heated, has a unique line spectrum that's like a barcode for that particular element. And line spectra are developed using diffraction gradients, and we did those in class. Okay, now Planck's theory, Max Planck in 1900, accurately predicted how the spectrum of an object changes with its temperature. So hotter objects change their temperature, and you've seen this before. It's called black body radiation, and we've talked about the you turn on your electric stove with all the lights out in the kitchen, and you'll see your electric stove start to get red, and that red is, and even to orange, and that color is characteristic of the temperature of your stove. Now, it can't really get hotter than that orangish color, but it also gives off light that is commensurate with that amount of energy. Okay, and here's the relationship, that the amount of energy given off is equals H nu. Okay, where E is the amount of energy that is absorbed. H is a constant, and it's called Planck's constant. Planck's constant. And it's 6.6262 times 10 to the negative 34th joule seconds. And those units are just there in order to create the amount of energy compared to when it's multiplied with the frequency of the radiation. Now, Planck's theory proposes that the energies absorbed or emitted by atoms are quantized, or in other words, they are restricted to certain quantities. And so if we think about this, if we know that, for example, if we know that hydrogen has this color line that has this really bright teal, okay, and then had this deep violet or a couple of violets, okay, and a red way over here, then each one of these would have a particular nu, or had a particular frequency. Now this frequency of light, okay, or this frequency of light, or those two frequencies of lights, okay, those colors, are going to correspond to a certain amount of energy. That energy, E equals h nu, okay, leads to the energy difference between electron level, energy levels. When electrons are doing their jumping around. Okay, and that's how we were able to go from the bright line spectra to predicting the model of the atom. Okay, now we finish with the photoelectric effect and the Heisenberg uncertainty principle. Einstein used Planck's equation to explain the photoelectric effect. He called these tiny pieces of energies photons, which are tiny particles of light. And mind you, this is what Einstein earned his Nobel Prize for, is this photoelectric effect. Not theory of relativity. He never earned one for theory of relativity. He earned it for the photoelectric effect. Okay, and here's what it is. The photoelectric effect is when light shines on a metal, certain metals, in this case a sodium metal, it ejects an electron from the metal, which can then be used to produce a small electric current. This happens with violet light, but not red light, even if the red light is intense. And why is that? Because if we come back over here to our formula, the frequency of light is related to the energy. And so if the frequency of light is strong enough, it's going to emit more energy. But if it's not strong enough, then the energy isn't there to eject an electron from the metal. Okay, and finally we have Heisenberg's uncertainty principle, which is sort of an idea that you need to know, but it's not. We're not going to test on it a whole lot. It's the idea that the position and the momentum of a moving object, an electron or really any other subatomic particle, cannot be simultaneously measured or known exactly. We can't know them both at the same time. Because of this, we can't really tell where an electron is in an orbital, or if we know exactly where it is, we have no idea where it's going to be next. And so there's a level of unpredictability to the motion of the electrons, and that is governed by this Heisenberg uncertainty principle. That'll do it for 5.3. It's a pretty short lecture for 5.3, and I know it's a lot of heavy physics and stuff that you haven't heard before, and so we'll be answering some questions on it later. And other than that, this is P-Dog signing off.